Thanks, Cynthia, for the introduction, and thanks to all the organizers, especially Christian. You can see there's lots of work to do. And for me, it's a pretty big honor to speak here. So my first FPSAC was when I was an undergraduate in Vancouver, so it's nice to be on this side for once. So this is going to be a talk about oriented matroids, and a tropical perspective on oriented matroids. So as we saw in Josephine's talk, matroids come up a lot in tropical geometry. And oriented matroids is kind of a real structure on a matroid. And we're going to try to find some definitions and applications to some real tropical geometries, especially in the realm of matroids. And then I want to generalize this to some more tropical varieties and call this patchworking in higher codimension. So to begin, I want to give a little bit of a background introduction to what is this patchworking of Oleg Virot. So this also came up in the very beginning of Josephine's talk. And this dates back to the 1980s. And it's a combinatorial method for constructing algebraic varieties up to topology. So I'm going to give the combinatorial side first and then get into the algebraic geometry theorem. So the combinatorial procedure is to fix some input. We'll fix a regular unimodular subdivision here of a size d dilated simplex of dimension n+1. And the second bit of input will be to choose a sign plus minus for every lattice point. So here I've got a two-dimensional simplex and a nice subdivision of it. And let's say that the filled-in vertices will be the plus ones, and the empty vertices will be the minus. And then the output of this patchworking is going to be some n-dimensional complex. So here a one-dimensional complex inside a projective space. Okay, so what do? We first take this simplex and take all symmetric copies of it in Rn. So just think I reflect this in all the coordinate hyperplanes, and I'll get 2 to the n+1 copies of it, and take the subdivision along with me. And then there'll be like a sign propagation rule. So we had signs in the kind of copy of the simplex in the positive orthant, the one we started with. You can see that the signs here match the signs here. And there's a rule for how to reflect the signs. Basically, you change the sign if the distance to the reflecting hyperplane is odd, and you keep the sign if the distance is even. So here, this white vertex becomes a black vertex. Okay? And then Virot's patchworking procedure says in these 4 copies now, just draw some curve, I'll draw it in red, that separates the pluses from the minuses. So just think 0 is between plus and minus. Okay, so let me shout if you see me make a mistake. I think this is good. Okay, so this is the polyhedral complex P. I've tried to draw it piecewise linearly. I kind of messed up here. I think these are all flat edges. You can think of this being supported on the barycentric subdivision of this subdivision that we started with. And to get something in RP2 in this case, okay, we have this square, just identify antipodal points of the boundary. Okay, so this is all very combinatorial, right? You choose a subdivision, you choose your signs. You get something that's topological, and Virot's patchworking theorem says that there exists then a homogeneous polynomial of degree d, which was the size of the simplex, and then a homeomorphism of pairs of the 0 set of that polynomial. That's the RVF. So in this case, there'd be a real algebraic curve, RVF, inside the corresponding projective space. And that pair should be homeomorphic to this P that we drew from the combinatorial patchworking and the corresponding projective space that we glued up by identifying antipodal points. Okay? So here's a picture of our P again, and here's some conic in R2 that we could glue up to RP2. Okay, we can see that it's not so shocking. They're both circles, but also their intersection properties with the axes happen to be the same too. So this existence of the polynomial is more or less explicit. So we can write down a family of polynomials in one variable t, using the information, using the combinatorial input that we started with. So this is one monomial for each lattice point. So we should think that this simplex that we started with was the Newton polytope of our polynomial. The signs of the coefficients are sign choices. And the coefficient is some parameter t to the alpha a, where alpha is going to be the function that gave us our regular subdivision. Okay, so it's important that this subdivision was regular in the sense that it comes from taking the upper or lower convex hull of some function on the lattice points. Yeah? What is the role of f? So the variety, this vf is the variety defined by f. So this is the zero locus, the solution set, the polynomial. Thanks. Okay? Any other questions? Okay, so this homeomorphism allows us to use combinatorics to study topology of real algebraic varieties. And this is a problem that goes back to, well, Hilbert's 16 problem and even before to the work of Harnack, so it's about 150 years old. And we actually know very little, even in the case of curves, or what are the possible topological types of real algebraic curve in the plane. So, Vierot's patchworking technique has been arguably one of the most, and its generalizations, arguably one of the most powerful methods for constructing algebraic varieties with prescribed topology. Okay? We can even just ask ourselves, you know, without caring about real algebraic geometry, but what's the topology of the complexes that we can get out of this procedure? And well, it's kind of limited. So for example, we would never be able to patchwork the empty set. If you have an even degree, you can get an empty real algebraic variety. But maybe more just topologically, there are the following theorems that came quite a few years after Vierot's theorem, is that if we obtain a hypersurface in this way, or if you think just the polyhedral complex P that we constructed, we know its Euler characteristic. So no matter what choices we make, no matter what subdivision, and no matter what sign choices, the Euler characteristic is going to be given by something called the signature of the complex algebraic variety. So signature in the sense of signature of the intersection form on a four-dimensional manifold. And if we're in odd dimension, the signature is always 0. So basically, just think we know the Euler characteristic. So you can't get everything that you want. And the second theorem of Renaud-Deneau and myself gives actually explicit bounds on individual Betti numbers of either, well, the real algebraic varieties that we obtain, or, you know, homeomorphically, this complex P that we obtained. So this BQ is the qth Betti number with mod 2 coefficients. When we're working with real algebraic varieties, things tend to be non-orientable. So it's much better to work with Z mod 2 coefficients. And the qth Betti number is bounded by the sum of Hodge numbers. So these are invariants of the complex algebraic variety. But by Danilov and Kovansky, there are very combinatorial formulas for this. Okay, so in the case of B0, which is number of connected components, the bound actually ends up saying that the number of connected components is less than or equal to 1 plus the number of interior lattice points of the polytope that we started with. So, okay, and well, we know from the limited examples that we have of algebraic hypersurfaces and their topology that these are very, very strict bounds. So there are hypersurfaces that violate these bounds that do not arise from patchworking. Okay, so I'm mentioning these theorems because at the end of my talk, I'm going to circle back to this in a generalization. The other reason why I'm mentioning this is because the second theorem here really came to us by shifting perspective on Vierot's patchworking to a tropical perspective. So it's just really a reformulation. But if we take this family of hypersurfaces that were given by this polynomial in T, Ft, okay, we can tropicalize that, as we saw in Josephine's talk. We'll get to tropicalization in a little simpler setting in a bit. But what we get is some polyhedral complex that's dual to the subdivision that we started with. So here we had our subdivision, and here's a picture of what the tropicalization of this hypersurface might look like. Okay, so it's dual in the sense that there's a order reversing isomorphism of the posets of the face lattices, but we also have to, it's a hypersurface, so we're not taking these regions here. It's something of one dimension less. Okay? And the second thing is, well, we could tropicalize remembering signs, and we would get something called the real tropicalization of Yael, Scheider, and Josephine. And this real tropicalization is also homeomorphic to P. So I've drawn the real tropicalization here, and you might recognize this. This is either the conic, or it looks also like the polyhedral complex P that we started with. Okay? And, well, to go from left to right, in the middle we have the tropicalization, and we might want to think, well, what is the real structure that we could put on the tropicalization to get this picture without doing this real tropicalization procedure, just patchworking like Veros. And that's simply to transport this sign data to the connected components of the complement, okay? So we kind of have an idea of what a real structure on a tropical hypersurface should be. Just think, put some pluses or minuses in the connected components of the complement. This is exactly what the sign data was here, the real data. The kind of motivational question that I want to ask is, well, what should, in general, beyond codimension 1, beyond putting plus and minuses in connected components of complement, right? In codimension higher than 1, we don't have connected components of the complement, or we have 1. They should be connected. What real structure should we put on a tropical variety? What should be a notion of a real structure? So here again, it's the sign choices in codimension 1, and for transversal intersections of tropical hypersurfaces, we can also use signs on the Newton polytopes of those hypersurfaces to get some sign data. This was a generalization of patchworking to complete intersections of Sturmfelds. But a lot of tropical varieties don't come as complete intersections. A lot of tropical varieties also don't come via tropicalization. So our main example of this is non-representable matroids. Do not give us tropical varieties which do not come from algebraic geometry. Okay, so we want a notion of real structure for those kinds of objects. All right. So matroids will be our next, our main example for at least the bulk of the talk. And well, we know that there are a real analog of matroids, and this is the oriented matroids. So these have come up in at least a couple of talks already. I'll give you another short crash course of what we'll need. So an oriented matroid for me in this talk will be given by its collection of covectors. Okay, so these will be a subset of E tuples of 0, plus, and minus, these signs. And they have to satisfy some axioms, and just as Vincent said yesterday, I'm not going to give you the axioms, and you don't want the axioms. They won't be very enlightening. What will be more enlightening is how to get an oriented matroid from a hyperplane arrangement, a real hyperplane arrangement, okay? So here I have 3 lines drawn in R2, and I should think that each line is given by some linear form, Fi. The ith line is given by a linear form, Fi. And what we're going to record is for all possible choices of x in R2, or in Rd in general, what is the sign of the linear form, Fi, evaluated at that x, okay? So, and sign being plus if it's positive, minus if it's a negative number, and 0 if the function evaluates to 0 at that point. So, for example, x at the origin, of course, all of those linear forms vanish, so we get the vector 0, 0, 0, okay? If we choose a point in here, I've denoted this region plus, plus, plus. This is the region where all linear forms are positive, okay? So we just go around and record, and we see that we get 1 vector for each cell in the subdivision given by this hyperplane arrangement. Okay? So what will be important are the so-called topes of M. So these are the kind of the covectors that have no zeros. These are the covectors that are just plus and minuses. And they correspond to these regions of top dimension, so regions in the complement of the hyperplane arrangement. And you know, here they look like polyhedra, or so topes is in a generalization of polytopes. Okay. Right, so rather than give the axioms, I want to give this descriptive theorem of Folkman-Lawrence, it's so-called topological representation theorem, that says that every oriented matroid can be represented by an arrangement of not hyperplanes, but pseudo-hyperplanes. So a pseudo-hyperplane arrangement will be an arrangement in, say, RD. They don't all have to be straight. There are some rules to the game, okay? But let me not give you those rules either. The representable case, where we actually have real hyperplane arrangements, is good enough intuition for our purposes. Okay, any questions? Okay, good. So we can, of course, go from oriented matroids to matroids by basically forgetting the sign data. Okay, so every oriented matroid has some underlying matroid, and the flats of that matroid is, okay, you take your covectors, the collection of all of them, and you map each covector to the complement of the support. So the zeros are the things that are interesting for the flats, or the things that give us the flats. Okay, so here's a slightly more basic example of an oriented matroid covector lattice. These covectors actually can be arranged in a lattice. Just the poset lattice of the faces of the subdivision of RD that we got from the hyperplane arrangement. All right, and then we see that the topes at the top, they have no zeros, so they map to the empty set, which is a flat. All right, and then we have multiple covectors mapping to the same flat, because they might have the same support, and so on. So if graphs and vector configurations and hyperplane arrangements provide examples of matroids for us, okay? Not every matroid comes from these examples, but these are certainly some of the richest ones. Then it's oriented graphs and vector configurations, hyperplane arrangements over the real numbers or any totally ordered field that gives us oriented matroids. However, not every matroid is orientable. Okay, the smallest example being the Fano-plane. So this is a rank 3 matroid on 7 elements that comes from all the points in the finite projective space over F2. This is not an orientable matroid, meaning that there's no oriented matroid which maps to it under this kind of forgetful map. Okay? And it's a theorem of Richter-Gebert that says that determining the orientability of a matroid is actually an MP-complete problem. Okay, so knowing whether or not you can go back, you should expect it to be very hard, or at least MP-complete. Okay, so as I mentioned before, matroids play a strong role in tropical geometry, and the connection here was first given by Sturmfelds in 2002, which says that every matroid, so whether it came from a graph, a hyperplane arrangement complement, or it was something that was not representable over any field, we can still construct a tropical variety of that. Okay, so this is where I'm going to say a little bit more about what these things look like on the next slide, give an actual description of it. But there's something that plays a role of a variety in this tropical geometry. And also, if we look at the tropicalization of a linear space, then what we get is only depends on the matroid associated to that linear space. Okay, so here's the example, exact same example from Josephine's talk, almost the same image. But so we'll start with this. This is an affine line in R2 defined over the reals, right? And when we're tropicalizing over C over R, we'll take this definition. There are other ways of defining the tropicalization, but this is just, you take the limit as the base of the logarithm tends to infinity of capital log base t. So this is just coordinate-wise, you take log base t of the absolute value of that coordinate. Okay? So if we kind of follow what this map does, right, turns out that, so for fixed t, before we go off to infinity, the most violent part of this map is the first stage, where we take the absolute value. Okay? So if we were just restricting, say, to the real positive orthant, taking log base t is a wonderful map. This is a diffeomorphism. Not only just homeomorphism, but it's a diffeomorphism. But once we go from here to here, we're folding all of the orthants up onto each other, okay? And that's kind of what ruins any idea of having a homeomorphism of what we get in the end. Okay, but so we can, after we take the absolute value, we take the logarithm, and we get something called the amoeba, and we let the base t shrink down to 0. Okay, but pointing out that if we restrict it to the orthants, we have a very, very nice map, because we're going to do this later. Okay. All right, but just for purposes of describing real structures later on, I do want to get a better description of what this set trop M looks like. And this set trop M can also be seen as the support of the Ardila-Clivens fan. So this is also known as the Bergman fan, but Bergman was studying logarithmic limit sets of algebraic varieties, not at all matroids. This is very related to tropical geometry, but Bergman was sort of in the context of the last slide where we took log base t of an algebraic variety. And this is something quite a bit more general, and it's not just a set. So what we have here is actually a fan structure on this set. So this is somehow more information. All right, so basically this fan given to us by Ardila and Clivens is the order complex over the lattice of flats of matroids, okay, embedded into R to the E in some nice way. Okay, so what that means is that for every chain of flats of our matroid, we're going to get a cone, and that cone is just going to look like the positive linear or non-negative linear combinations of the, well, here I'm taking minus the indicator vectors of each set. It's just my convention. Okay? So just think we have a cone for each chain of flats. And it is important the directions it's put in into Rn in order to conclude the last remark on this slide that says that this projective Ardila-Clivens fan, so this is just, I take this image of this fan with the tilde on it in the quotient of a vector space, okay, by the all ones vector. That this is a Minkowski weight of the permutahedral toric variety. So basically it means that with these directions put on the cones, that there's a balancing condition that's satisfied that links us to both tropical and toric geometry. Okay, so if you're familiar at all with the program of Junhe and many collaborators, it is this key fact that all of the matroid fans, if we have that have the same ground set, live as cohomology classes in the same cohomology of the same toric variety. So intersecting them gives us many matroid invariants and has resulted in many applications and understandings of matroids. Okay, so what I want to do is kind of take this and upgrade it to an oriented version, basically, with hopefully similar applications coming from toric geometry. All right, so here's how we're going to encode a matroid orientation on this fan. Okay, so we have some mathcal M, which is an orientation of M. That means the underlying matroid is M. And we define for every cone in this fan, the Ardila-Clivens fan, the following set. So it's going to be a set of topes. So these are a set of plus minus E tuples. And the so-called topes of the oriented matroid that are adjacent to the flag. Okay, so here if I take the flag to be just the single flat, 1, 2, 3, so that's this point here. Okay, adjacent means the tope has to literally touch just that single flat. So that's everybody, all of these 6. Okay. Now if I take a chain 1, 1, 2, 3, I'm going to ask that not only do the topes have to touch 1, 2, 3, but they have to touch both 1 and 1, 2, 3. Okay, so then I would get this tope, this tope, this tope, and this tope. Okay, these 4. And the 3 and 1, 2, 3, we would get these 4. Okay. Literally, if you look at the corresponding pseudo-hyperplane arrangement, it literally means it has to touch that flat. So the taupe is a maximal codimension cell. It means it has to have a face of the cell, which is contained in the subspace given by the flat. Okay? If I could draw an example nicely in higher dimensions, you would see that it gets more interesting as I take different chains. So for example, if I just take 1 here, instead of 1, 1, 2, 3, I actually get the same set. Okay, but let's ignore that for a second. That's just the fact that we're in very low dimension. This doesn't always happen. Okay. And sort of similarly, but just people that maybe are more algebraic geometry tropicalization minded, we could also start from a linear space, L in a vector space Re. And then I have the tropicalization of L, which I said this, the tropicalization is the support of this fan. Okay. Now we can also define a collection of plus minus vectors for each cone then of that tropicalization using the real tropicalization ideas of Yell, Scheider, and Yu. So this is going to be, take the set of all plus minus vectors such that if you take that tropicalization map and instead of doing it on all of R to the E, right, which was bad because the absolute value crushed everybody up and it wasn't a nice diffeomorphism, restrict it to the orthant corresponding to the sign vector of this epsilon. Okay? And when you restrict it, you can look, well, what's the image? What do I get then just in that orthant? And if your cone appears in the tropicalization of that orthant, then you stick that plus minus vector in this set. Okay? These are complete, when the two definitions overlap, they're completely compatible. They're the complete same thing. All right. So let's look at what such a map, the structure of such a map is. So here notice, well, these taupes, there are 4 of them. That's 2 to the power of 2. Okay? And well, plus minus, we're not used to thinking of plus minus as a vector space, but as a field, sorry. But under the following identification, right, where we think of plus as being 0 and minus as being 1, then we can make plus minus into a field, the field of 2 elements, binary field. I've chosen Z mod 2 instead of F2 just because people in real algebraic geometry use Z mod 2, and I just, yeah. Okay, or think F2. Okay, so then this plus minus to the E inherits the structure of a vector space. Okay? Looks kind of weird because adding, plus, plus, plus and minus, plus, plus is actually coordinate-wise multiplying. Okay, you get me? All right. I've tried to hopefully use both approaches, and let me know if you get confused, because I think this is, and it's not very confusing, it's just a field isomorphism. All right. But notice that then, if we took these collection of taupes that we found from the other side, under this identification, this collection is actually a vector space over the field of 2 elements generated by V1 and VE, so the entire set. You with me? Yeah? Yeah.
So it feels like plus and minus play a symmetrical role in your original picture, but in the field of 2 elements, obviously they don't. That seems kind of confusing.
So you're saying that 0 doesn't seem to be very important, and in a vector space, I would say, well, then it's like the origin is not very important, right? In a sense. So let's look at this one then. Well, this one is not a vector subspace. This is an affine vector subspace. Okay? So, and there's nothing more special than this one, that one is a vector subspace and one is an affine vector subspace. So literally here, the observation is that these two are both affine vector subspaces of the field of 2 elements to the power of E. Okay? And that's the lemma. So this fact actually generalizes if you have a facet, so a top-dimensional face of the fan, then this set that there should be an M here, or an L if you like, but then the set that we just defined is an affine subspace of this weird vector space plus minus to the E. Okay? And also if we take a lower dimensional face, so some tau F for some non-maximal flag, so non-maximal cone, then, well, that set is just the union over all of the facets. So it's a union of affine vector spaces. Okay? And if you think about it, when you have a maximal chain, this being adjacent to, literally what it means is if you start with one tope that's adjacent to everybody, what you should do is you should reflect in all of the subspaces that are in that chain. And that's how you get all of the topes. So this reflection is really, generated by these vectors, adding these vectors. So here's a sort of a definition of real structure on tropical varieties, but let's say it's a 1.0 definition. So I think there should be generalizations of it. So if we have a fan that's of dimension D, what we want to do is have a map, capital E, that assigns to each face an affine vector space of dimension D to this vector space over the field of two elements. And it has to satisfy two things. One is that for each face, this affine vector space should be parallel to the face that we started with when we reduce mod 2. Okay, so this cone here, its directions were V1 and VE. And the directions here are V1 and VE, but reduce mod 2. And the second condition, this is sort of a real balancing condition. If you know the balancing condition in tropical geometry, I want you to try to think of this as a real analog. It's that if you look at every codimension one face in the fan, and all of the facets that are adjacent to it, right? So we have an affine space over the field of two elements for each one of those top-dimensional faces. Well, I want the multi-set, I take the union of all of those, but as a multi-set, I want it to be an even covering. That means every element of the vector space appears an even number of times. That could be 0, or that could be 2, or that could be 4. So here's an example. I could put, say, minus, I'm in R2, so I need to put a 2 tuple of signs. So this is parallel to this horizontal direction, this pair. A vector space of dimension 1, or an affine vector space, has 2 points in it. Right? It's also a finite set. That's one I could put here. Okay? And now I can think about this as being, I've selected this pair for the horizontal face. And now I'm thinking of these as 0, 0, 1, 1, 0, 1, 1, 0. Okay? This is a set Z mod 2 to the 2. And now if I want to take the last pair of signs on this face, I need to satisfy this even covering condition. And I need to satisfy that it has to be parallel to the face. So there are two vector affine spaces parallel to the diagonal. There's this one, and there's this one. So this and this are parallel over F2. Okay? So, yeah. So, if you're, and which one then should we take to get the even covering condition, right? Well, this one we can't because then we've covered somebody only once and we've covered some people 3 times, but we can take this pair. So which means that we should put minus, plus, and plus, minus on this face, okay? So that's a balancing condition. All right. Here's a main theorem, is that if we put one of these real phase structures on a matroid fan, it's the same thing as giving a matroid orientation. Okay, so we saw how to get a matroid from a matroid orientation to one of these maps. So we have to check that this map satisfies condition 2. I hope I convinced you that it satisfies condition 1. To go the other way, if we start with one of these strange maps that satisfies the parallel of the affine spaces condition and the real balancing condition, then we need to recover an orientation of the matroid. So the argument that we give in our paper is very non-explicit, but uses a deletion contraction argument, and we also give a description of the signed co-circuits. But here's how you kind of do it. You notice that if you have the real phase structure, this map, then you can also get real phase structures on the deletion and the contraction. So think that this is just, you remove one hyperplane from your arrangement to get the deletion, or you restrict the arrangement to a hyperplane to get the contraction. Okay? And then you use a double induction argument to say that, okay, and you prove some base case, to say that now we get a correspondence, so we get orientations of these two matroids from those real phase structures. And then we do a bit of work to verify that the orientation on the deletion, the restriction, is a quotient of the orientation of the contraction. So oriented matroid quotients and also that this would be a co-rank 1 quotient. And co-rank 1 oriented matroid quotients satisfy the extension property. We saw an extension property come up in Carolina's talk. Okay, she was asking a question if for positroids, if they satisfy the extension property in all ranks. Oriented matroids don't satisfy an extension property in all co-ranks, but in co-rank 1 they do. So we can use this to cook up an orientation of our original matroid M, which is the matroid extension of these two. Okay, and then we show that the orientation that we've cooked up actually is the same as the real phase structure of the orientation we cooked up is actually the same as the one we started with. Okay, so it's not a very explicit argument, but it is made more explicit with co-circuits in the paper. All right, so what can we do with this real phase structure now? So we have a cryptomorphic definition. Okay. That could be interesting on its own, but I want to try to convince you that there's some kind of topology that we can get out of this, and hopefully some applications. So when we have a real phase structure, what I want to do now is do a patchworking procedure like we did in the very beginning with Oleg Viro. So we have these two pieces of information on the left. We have, say, the fan of a matroid that we started with, the projective fan. And we have a real phase structure on it. So I've drawn this as I did in the other way. So the horizontal line gives me the pair of signs on the horizontal edge, and vice versa. Okay. So we're going to build something in this disjoint union of a bunch of copies of Rn and one copy for each sign vector. Okay. So think of these are the orthents. So here I have the plus orthent, but this whole thing is actually R2 stuck here. Okay. And this is the minus plus, let's say. Okay? And I take 4 copies of the line, but I only take the faces if by this rule. So if I have a face of the fan, I only take the corresponding copy for the sign epsilon if epsilon is in the E of that face. Okay? So that means that here where I had a minus plus and a plus minus, we see that that's exactly where this diagonal edge shows up in its symmetric copies. Okay? We good? So this is something that's living, it's something that's living in disjoint union copies, 2 to the n disjoint union copies of R to the n. Okay? But this here is also homeomorphic to R star to the n. So again, R maps to R positive by the exponential map. Okay, so just in case you want to rather think about tropicalization and real tropicalization, what we've just this proposition just says what we've just constructed is the real tropicalization of Yell, Scheider, and U. Okay, so if we tropicalized orthent by orthent, we would get this picture. Okay, but if we have a matroid, an oriented matroid that doesn't come from a real algebraic, real linear space, then we have something new here. And in fact, this was kind of the real part of a matroid fan was sort of also considered by many others. I mean, not in this language by Las Vagnes, but certainly the face order complex of the face lattice was. But this theorem tells us what this patchworking thing looks like when we close it up in different places. So if we look at the positive part, I should be careful. This is going to be either empty, as it was in our last example. Okay, it's either empty, or it's homeomorphic to just Rd plus 1. Okay, where D plus 1 was the rank of this matroid, at the dimension of this fan. We could also take the compactification by adding back in the kind of, what would look like the zeros if we were thinking about R star to the n, and the compactification is still Rd plus 1. Okay, so topologically, these aren't the most interesting things, but what's kind of nice is that this gives us a sort of tropical Folkman-Lawrence theorem. If we look at the subcomplexes, when we intersect with these axes, we get a pseudo-hyperplane arrangement on this Rd plus 1, okay, and it's equal to the, its associated oriented matroid is the one that we started with. Okay, so this is kind of a patchworking of oriented matroids. I should point out there's also a evaluated version of this by Saleha Loho and Chiho, who's here, I hope. Yeah. And I think also maybe to appear of Alarte, Rincon, and Smith. For those that might be interested in relative topology, so I think this is something that hasn't been asked yet. So in Virot's original theorem, it was a homeomorphism of pairs. So the first theorem is just talking about what does the space itself that we've built look like, not how does it sit in Rn. And I don't actually know. The closest thing we have, which is this sort of theorem that we proved for follow-up work with Renaudino and Rao and myself. And it says that if instead we look at the compactification of the projective Bergman fan when we patchwork it, we look at the positive part in the positive part of real projective space. Then this pair is a standard pair of disks. Okay? And there are other fans as well. So this was actually, you would think that this, and this is in the realizable case. We didn't need it beyond that. And I think it should be true, but I don't know how to prove it. There are certainly compactifications of these things that we can take which are not standard pairs of disks. I think we see some in Leo's talk. But another question that I want to ask is that we can now also patchwork different matroids on the same ground set in the same place. And what do their topologies look like? So if we have a oriented matroid quotient, its patchwork should sit inside the patchwork of the other matroid. And I really wonder if beyond co-rank 1, if there are some wild embeddings. And I think I have some ideas of where we might look, where the matroid extension, oriented matroid extension problem fails. Okay. So here's just a description of how we can look at the real part of an oriented matroid in other real torque varieties. Okay, so I said that thing we patchworked is living in this 2 to the n disjoint copies of Rn. And this is actually homeomorphic to a real torus. You can compactify the real torus in many ways to different real torque varieties. There's a very explicit combinatorial way of doing this. I'm not going to give it to you. But then we can consider the closure of the thing that we built in these other real torque varieties. So for example, we did this in Rn. We did this in Rpn. We could also do it in Rp1 to the n. This is Leo's matroid Schubert varieties. I imagine there's some details to work out that they're the same thing. We could also do it in the real permutahedral torque variety, which is the place to look at Minkowski weights, not over the reals of matroids. Okay, so what's nice about the conditions to be a real phase structure is the following proposition, that if you do this patchworking, the conditions R1 and R2 imply that the thing that you build will give you a closed cellular chain in this real torque variety. So it gives you a homology class, which I've denoted like this. All right? In a sense, there's a kind of partial converse that if you're interested, I can tell you what the partial converse is. So these conditions are, in some sense, almost necessary with there. I mean, there's some little generalization to tweak it to make it an if and only if. Okay. And with that cohomology class, we can formulate a kind of nice homological obstruction to matroid orientability that comes to us from toric geometry. So if M is a matroid on the ground set E, right, then this Ardila-Clivens fan that we constructed is always a subfan of the permutahedral fan. Okay? And there's occlusion of toric varieties then. So even if the matroid doesn't exist, or isn't representable, sorry, it exists, then you still have the fan and the toric varieties, and you have this inclusion map. And you get an induced inclusion map on the homology. Okay, so if the map is not 0, this theorem says that M is not orientable. Sorry, if the map is 0, the matroid is not orientable. Okay, so there are cases like the Fano-matroid where this map ends up being 0, so this gives us an obstruction to the orientability of the Fano-matroid. I don't know to what extent the converse of this holds, but the other kind of unfortunate thing, though, about this map, if we want to think about having different orientations of the same matroid playing and hanging out in the same ring under this map, okay, the image of this map is either 0 or 1. So it means that no matter what orientation you have of a matroid, they're going to go to the same place here. Okay, it's basically the class of the matroid. It does not remember the orientation. If this map is 0, then the matroid is not orientable, but if the matroid is orientable, any orientation that gives you a class here goes to the same thing here. Okay, so it's not the place, it's not as rich as the theory of Minkowski weights of non-oriented matroids. There should be another place to look at this. Okay. Just want to say, do I have 3 minutes? Yeah. Okay. I just want to say a little bit about going beyond the matroid case and going beyond codimension 1 case for patchworking. And this was kind of our original reason of looking at topologies of these the pairs of the real part of a matroid fan in a real torque variety, because we wanted to extend this to beyond just the fan case to notions of a real structure on any tropical variety. So if we have a d-dimensional polyhedral complex, we can just take this same definition, and it should be a rational polyhedral complex because we want things to be parallel to vector spaces over F2. We can generalize this definition of this map for a real phase structure. So we just keep the properties 1 and 2, and it didn't matter if it was a fan or not, it still has some condition that has to hold on each facet and each codimension 1 face. Okay? And then we can similarly construct the real part, so patchwork it together in these 2 to the n copies of the ambient space. And the theorem says that if we started with something that was locally matroidal, and we had a real phase structure, okay, we should think that locally this thing is an oriented matroid. When we patchwork it together, we still get a PL manifold. We get a piecewise linear manifold. And the bounds on the Betty numbers that we get, that we saw from the hypersurface case, these can also be generalized to give us bounds on the Betty numbers here, except that instead of Hodge numbers, because here we have no algebraic variety hanging around, something called the tropical homology numbers, the dimensions of the tropical homology groups. Okay, so definitely skipping the proof. It was just some points. Okay, but you can ask about it in the end. And going back, circling all the way back to algebraic geometry again, we were able to prove a kind of generalized patchworking homeomorphism theorem in the way in the style of Viro, but missing kind of the most magical ingredient of it. But let's just say what it is. So if we have a family of algebraic subvarieties over of a torque variety over the disk, and the tropicalization is again locally matroidal. Okay, if it's locally matroidal, then we can get it's defined over the reals too. It's locally oriented matroids. We can get a real phase structure of it. And when we patchwork this thing together, we end up getting a homeomorphism of pairs of the real patchwork part. So this is the combinatorial thing that we build from the tropicalization and the real structure. And this is for a sufficiently, not large, sufficiently small, sufficiently small positive T, sorry. We get a homeomorphism of the pairs of the real torque variety and this algebraic variety. And we also get bounds on the individual Betty numbers, again, coming from tropical homology groups, and we get a relation on the signature and the Euler characteristic. So I'll stop there, and thanks.
Okay, questions for Kris?
Yeah, hi. I'm wondering if there's any connection to these tropical ideals of McLaughlin and Rincon?
If we've looked at the tropical ideals,
Yeah.
do they have a real notion of this? Or?
I guess not yet. Maybe.
Yeah, not that I know. Like, do you mean because okay? So they have a lot of things about tropical ideals and matroids.
I can imagine the setting should be easy to generalize to oriented version, I would think.
Yeah, I don't know. That's a good question. Something I'll ask Felipe. Thanks.
Yeah, so I suppose your last theorem generalizes Sturmfield's theorem for complete intersections.
Yeah, exactly. And I mean, so if...
I figured that.
Yes, exactly. There are kind of tropical complete intersections that don't fall into Sturmfeld's scenario, but that do fall into that scenario.
But I guess there's nothing about it needing to be complete intersection here.
Yeah, exactly. Yeah.
Can you say a word or two about why locally matroidal is like the right condition?
Yeah, so I think I'm the wrong person to ask because I'm starting to think that I think it's the right definition because it's the one that we've been believing for a long time is the right definition. So when in tropical geometry, matroids behave like linear spaces, or they are the local pieces of linear spaces. And if you want to, so there's a notion of tropical manifold, right? And a manifold should be a space that has charts to, well, let's say Euclidean manifold to Rn, and it should have nice transition functions. So the first kind of idea for a tropical manifold is, okay, you should have charts to linear spaces. The problem is linear spaces look different. They're not all homeomorphic. Okay, but then, so that's a great first proposition. And then the fact that actually their geometry is incredibly, it's unbelievably nice. These things have Poincare duality for the tropical homology theory that I mentioned. They have equivalence of A and Cartier divisors. They have all kinds of things that you would expect of smooth spaces in algebraic geometry. But I think that we've been a bit too tunnel vision because I think there are other fans that say satisfy the Kähler package of Junhe and collaborators, or that satisfy all these other nice properties that we've just kind of left by the wayside. And I think a really interesting question is to kind of classify what are the fans even that have the Kähler package and stuff like that. And there are extra, so there are other things out there.
Okay, let's save the rest of the questions for the break and thank Kris again.